In this example, we're going to be using a stress-strain diagram for steel alloy. We have a y-axis in megapascals for the stress, but because we want to put this all on one neat graph, we're going to use two x axes, basically, that are superimposed on each other. The first one you see in red, that is the start of it, okay, going through its elastic phase. And then you can see where it stops at 43 on the right there, and then it'll continue again at that value in the blue line. So it's just overlapped on each other, makes it a little bit more organized, okay, a little neater for this problem. So this is a steel alloy, and it has a radius of 3 millimeters, the sample, and it has an original length of 250 millimeters, and it is subjected to the stress, and you see the recorded strain resulting. So the first thing we want to do is calculate the modulus of elasticity, okay? And that's in the beginning portion there on that linear straight line. And to calculate that, we have to, which is E is equal to the stress over the strain. So we're looking for the slope. So in this case, the very top point there, the delta between the beginning and the end at that point is 40 megapascals for the stress. And if we go down on our, down to the x-axis, we can see that it has a strain of 0.001 millimeters over millimeters. This equals 40.0 times 10 to the third megapascals, which would then give us a modulus of elasticity for this sample of 40.0 gigapascals. The next property of this steel alloy sample that we want to calculate is called the modulus of resistance. And this is essentially the area under that first section there, that little triangle area. Next, we want to find the modulus of toughness, and this is the area under the entire curve. It is how much total energy the sample can absorb up to the point of failure. Now, this again is somewhat approximate and can be done with, like we did before with the triangle. It can also be done by counting up the number of squares that you see there. And so we add all these areas up, and we get a total of 18.55 megapascals. The last thing we want to calculate for this sample is what is the length of this cable or sample when 1,000 newtons is applied, and in this case in compression. So the first thing we want to do is calculate what kind of stress this sample is under. And so we're going to use the formula of normal stress, which is the force over the area, and we have a 3 millimeter radius. So it's 1,000 newtons divided by pi times 3 millimeters squared. And we get a stress of 35.37 megapascals. And if we look at our stress-strain diagram, we can see that this clearly falls in the elastic range. So there's no permanent deformation. And so we can use the modulus elasticity, which will help us solve this, because the modulus elasticity in this range is consistent. Okay, and the modulus elasticity again is stress over strain, and we can flip that because it's constant through this area. So then we'll have the strain, which we're looking for this sample, divided by its stress, which is the 35.37, and that's equal to the strain at the point of yield, which is 0.001 divided by 40, which is the stress yield. And we can solve for the strain that is occurring at the 1,000 newtons. And we get 0.000889 millimeters per millimeters. And now using this, we can solve for what the new length is, okay? And the new length is equal to the original length minus the strain times the the original length, and that gives us a new length of 2.49.78 millimeters.